In this video, I want to look at eigenvalues and how to find them. In my last video, when I talked about eigenvectors, I was solving this equation a minus lambda I x equal to 0. And we need x to be non-zero in order to be an eigenvector. Since this needs to have a non-trivial solution, a minus lambda I must have infinite solutions. It's the only way for it to work. If it doesn't have infinite solutions, then x must be equal to 0, which violates my condition for an eigenvector. So what we need is the determinant of a minus lambda I to be equal to 0, since this is the same thing as being non-invertible, which is the same thing as having an infinite number of solutions. And this is known as the characteristic equation, or the characteristic polynomial, since it will end up being a polynomial that we need to solve. So let's look at some examples. Here I have my matrix -4, 2, 6, 7. To find my eigenvalues, I need to find the determinant of a minus lambda I. And like we mentioned in the last video, subtracting lambda I means just subtracting lambda from the diagonal. So I have -4 minus lambda, 2, 6, and 7 minus lambda. Taking this determinant, we have -4 minus lambda times 7 minus lambda, minus 12, and we need this to be equal to 0. This is -28 plus 4 lambda minus 7 lambda plus lambda squared minus 12. Rewriting is lambda squared minus 3 lambda minus 40 equal to 0. This factors into lambda minus 8, lambda plus 5. So my eigenvalues are 8 and -5. So I'm going to write this up here. We have lambda equal to 8 and lambda equal to -5. Now that I have my eigenvalues, let's find the corresponding eigenvectors. I'm going to start with lambda equal to 8. So we subtract this from the diagonal. -4 minus 8 is -12. 2, 6, and 7 minus 8 is -1. When we reduce this matrix, we get 1 minus 1/6, 0, 0. Therefore, my equation is x1 minus 1/6 x2 equal to 0. Solving for x1 is 1/6 x2. When we make our vector, we have that x1 is 1 over 6 x2. x2 is a free variable. We can factor out the x2 and we get our eigenvector of 161. And like I said in the previous video, we really like to go ahead and multiply through by common denominators to get 1/6 to be our eigenvector. So the eigenvector for lambda equal to 8 is 1/6. Now let's find the eigenvector corresponding to lambda equal to -5. -4 minus -5 is 1, 2, 6, and then 7 minus -5 is 12. Reducing this gives me 1, 2, 0, 0. When I write my equation, I have x1 plus 2x2 equal to 0, or x1 equal to minus 2x2. So when I write my vector, x1 is minus 2x2, and x2 is my free variable. Factoring out the x2 gives me -2, 1. So now my eigenvector corresponding to -5 will be -2, 1. Let's now find the eigenvalues and eigenvectors of this matrix. We start with our determinant. We subtract lambda from the diagonal, so I have 3 minus lambda, 4, 6, and 1 minus lambda. We multiply to get 3 minus lambda times 1 minus lambda, minus 24, and this should be equal to 0. This is 3 minus 3 lambda minus lambda plus lambda squared minus 24 equal to 0. That's lambda squared minus 4 lambda minus 21 equal to 0. This factors into lambda minus 7 and lambda plus 3. So my eigenvalues will be 7 and negative 3. So we have lambda equal to 7 and lambda equal to negative 3. Let's try to find the eigenvector corresponding to 7. We need to subtract this from the diagonal. So 3 minus 7 is negative 4. 4, 6. 1 minus 7 is negative 6. We row reduce this to get 1 minus 1 in the first row and 0, 0 in the second. That gives me x1 minus x2 equal to 0, or x1 equal to x2. So my vector, the equation for x1 is x1 equal to x2. x2 is a free variable. Factoring out the x2 gives me 1, 1. So the eigenvector corresponding to lambda equal to 7 is 1, 1. Now let's look at lambda equal to negative 3. Subtracting this from the diagonal, 3 minus negative 3 is 6, 4, 6, and 1 minus negative 3 is 4. We can row reduce this to get 1 2/3 in the first row, 0, 0 in the second. So my equation says x1 plus 2/3 x2 equal to 0, or x1 equal to 2/3 x2, or minus 2/3 x2. So the equation for x1 will be minus 2/3 x2, and then x2 is a free variable. Factoring out the x2 gives me negative 2/3, 1. And we'll go ahead and multiply this by 3 to get my eigenvector of negative 2, 3. Our big theorem with eigenvalues is that a matrix A has an eigenvalue of 0 if and only if A is not invertible. So we're actually going to prove this. First, we're going to assume we actually do have an eigenvalue of 0. We know we need to find A minus lambda I times x equal to 0. Since lambda is 0, this whole thing right here is going to be 0. So this is the same thing as ax equal to 0. We know we must have infinite solutions to this by definition of the eigenvector. Therefore, A is not invertible. If it was, we would only have the trivial solution. The second piece to this, let's assume A is not invertible. Then we know that ax equal to 0 has an infinite number of solutions. And we can also rewrite this as ax equal to 0 times x, since we know that 0 times any vector is equal to the 0 vector. And this is the definition of 0 being an eigenvalue.